now we have John Wickerson from Imperial College London, who is a senior lecturer there at the Department of Electrical and Electronic Engineering, and his research is at the intersection of programming languages and hardware design. Thank you.
Thank you for the introduction. So to set a bit of context, first let me say this is a whole load of joint work with my students, Yann, Michalis, and Quentin, and a bunch of other collaborators, mainly from Imperial. I want to set a bit of context so we know that we're talking about the same thing. I'm talking about the tools that make these things do things, ASICs or FPGAs mainly. You might have got your FPGA to do something by using a place and route tool or some other physical layout tool by giving it a Verilog netlist. You might have got your Verilog netlist from a logic synthesis process, perhaps having written some Verilog RTL. You might have got your, you might have checked that your Verilog RTL is equivalent to some specification that you or somebody else wrote in perhaps System C. And you might have used an equivalence checker to see that these line up. And you might have also got your Verilog RTL by writing first your specification as a C program and then using a high-level synthesis tool, HLS, to produce that RTL. So this is the kind of context for this talk. I'm talking about high-level synthesis, equivalence checkers, logic synthesis, and a tiny bit on place and route. And my overarching thesis is that all of these tools are too buggy. They're too buggy, but there is hope. Because with more rigorous engineering, they can be made more suitable for safety and security critical settings. So that's my thesis. To demonstrate my thesis, I'm going to go through the four tools and tell you a bit about how buggy they are. And I'm going to start with high-level synthesis. This was the work of my former PhD student, Yann. So high-level synthesis, we're talking about taking perhaps a C program, it might look a bit like this, and turning it into this unreadable horror of Verilog RTL. Okay, you can see why high-level synthesis appeals to people, because I would much rather write this than write this. But do the high-level synthesis tools do the right thing? Can they be relied upon to always produce correct RTL? Well, to try and establish this, we generated a whole load of random C programs. So C programs that don't do anything particularly interesting, but they are nonetheless legal, valid C programs. And that's all they are. So we generated those and we gave them to 4 HLS tools that we could get our hands on. So that was 2 commercial tools, one from Intel and one from Xilinx, and 2 open source HLS tools, LegUp and Bamboo. And this is what we found. So it's a slightly complicated diagram to unpack, but what it is it's basically a Venn diagram. Down here are most of those C programs, and these are the C programs that didn't cause any problem. So about 80% of them passed through all 4 HLS tools fine, no problem. But the ones in these circles are the ones that caused the tool to go wrong in some way. So we see here 27 of those C programs caused a problem in the Intel HLS tool. 26 of them only caused a problem in the Intel tool. 1 of them caused a problem for both Intel and for LegUp. So that's these intersections here. And when I say go wrong, I mean either the HLS tool crashed in an ungracious way, so like a seg fault, that kind of thing, or silently produced RTL that was just not equivalent to the C program. Okay. And one quick shout out for open source tools. You see here Bamboo, which is one of the open source tools that we tested. Initially, version 0.9.7, it's losing. It's 902 plus 3 plus 9 plus 4 of the test cases are crashing or miscompiling in Bamboo. So that's initially not doing very well. But we reported this to the Bamboo developers, and within a day or two, they'd fixed a couple of the underlying issues in their tool. And we retested it with the newer version, and suddenly Bamboo is now top of the charts. It's now got the fewest failures. So that's a win for open source there. I want to give you a quick flavor of the kind of bugs that we were finding. Here is an example of a C program that came as a result of this random generation process. we reduced it down to this form. So this C program, if you give that to leg up 4.0, it will cause it to crash, like segfault. If you give this C program, slightly longer, still pretty short, you give that to Vivado HLS several years ago now, and it will silently produce RTL that is not equivalent to that. And just one more picture I want to show you. This is a little bit of an indulgence, but I quite like this picture. What this is showing is we've tested 3 successive versions of the Vivado HLS tool, one from 2018 and 2 from 2019. And the black bar is the total number of test cases that crashed or miscompiled. Okay, so you can see the most crashes and miscompilations were in the 2018 version, slightly fewer here, slightly more there. But these colored ribbons are tracing the same set of test cases through those 3 versions of the tools. So this bar at the top, these are the 31 test cases that went wrong on all 3 versions. This light green bar is the 26 test cases that went wrong in the 2018 version, but then they were fixed by the time of 2019. So that's good progress. And my favorite bar, though, is the blue one, because this is about 4 test cases that failed in 2018. They were fixed for 2019.1. And then somehow, I have no idea what's going on here, but somehow they were broken again by 2019.2. Okay, so in short, these HLS tools, perhaps not as reliable as we might like to hope they are. Can we, therefore, improve this situation? Can we have more reliable HLS tools? Well, what Yann did is he built a tool called Verisert. Verisert is built upon an existing tool called CompCert. CompCert is a C compiler developed in France. And what's special about CompCert is that it is entirely programmed inside a mathematical proof assistant, which means it comes with a mathematical theorem that says it has no bugs. If it produces an output, that output is mathematically guaranteed to be equivalent to the input. So we took CompCert and we kind of tapped out in one of the intermediate languages and added a sort of HLS-specific optimization and a Verilog backend and said, there we go, that is now an HLS tool. And it comes with a complete guaranteed mathematical theorem of correctness that I'm not going to unpick the whole thing, but it basically says if you run HLS on a C program, C and HLS process completes okay and gives you Verilog V, and that C program is safe in the sense that it doesn't have like divide by 0 nonsense, that kind of thing, then any behavior of the Verilog program will also be a behavior of the C program. They behave the same, basically. And it was quite a bit of effort. Yann wrote quite a lot of stuff and quite a lot of proof. So we've proven it correct. That's great. But Donald Knuth has a famous motto where he says, beware of bugs in the above code. I've only proved it correct, not actually tried it. So we thought, well, since we've got this framework for testing all of these HLS tools and finding bugs in those tools, we'd probably better sort of turn that on our own tool and make sure that this mathematically proven correct HLS tool doesn't have bugs either. So we did that, and it went fairly well, but not brilliantly. So in the sense that we generated a whole loads and loads of randomly generated C programs. About a quarter of them passed fine. This is good. Most of the rest of them gave a compile time error. This is okay. This one's okay. I can get away with this because the theorem says if compilation completes and it produces a result, then that result must be correct. It doesn't say it will always produce a result. It's always allowed to error out and say, sorry, I couldn't compile that. Okay, so that's just a case of our HLS tool doesn't handle all of the complete C language. Okay, so this is not a concern for us. This one was upsetting. This was 39 of them actually caused an error. So what happened here? Turned out, as is often the case with these mathematically proven things, there's a bit where you have to interface between the beautiful maths and the dirty environment, the real world, the pretty printer, basically, or the parser. And this is where bugs can still lie. And it turned out, and Yann hates me for always talking about this, but there turned out there was a bug in how he'd written the pretty printer. There are 2 operators in Verilog for doing logical negation. One is an exclamation mark and one is a tilde. He confused the 2. That led to a bug. He fixed it, and now there are no more bugs. So we think it's okay. But yes, sorry, Yann. He also checked performance. So we've got correctness nailed down. How does it perform? Does it generate decent hardware? We used a standard benchmark. Most of them were applicable. We synthesized for FPGA, measured area and running time, compared against LegUp, which is an open source HLS tool, and again, just quick glance at the graph. This is a bunch of benchmarks along here. The graphs show the performance of the hardware generated by the tool. And roughly speaking, we see Verilog, which is the green bars, is doing fairly similar to the orange bars, which is leg up when you've got similar optimizations enabled. In short, performance isn't great, but correctness is as good as it could be. It's all open source. Go find it on GitHub, and we wrote a couple of papers about it. And there's future work on it as well. Okay, so that's high-level synthesis. I want to talk next about logic synthesis, so a bit further down in the tool flow. This was also some work done by Yann and also my other PhD student, Quentin. The story is actually fairly similar. We generated a whole load of random Verilog designs. They don't have to do anything, but they have to be legal and valid. Here's an example of one of them. I'm not going to go through it, but you can see it declares a whole load of nonsense wires, does a whole load of nonsense assignments, and we pass them all into a whole bunch of logic synthesis tools, including open source ones like Yosis, Vivado, XST, and Quartus Prime. Found a moderate number of them failed. We were able to isolate a handful of bugs in each tool, reported them, confirmed, all very good. One bit I just want to focus on here in this table is that for Quartus Prime, we failed to find any bugs at all. We found bugs in everything else we tested, but we have never to date found a bug in Quartus Prime, which is a bit annoying to us and quite pleasing to the people at Intel who we told that about. Sure. We did find a bug in Prime Lite, but that's a slightly different piece of software, and it had a bug relating to sign. And an example of a bug we found, this was so Vivado, or at least a couple of versions ago. If you gave it this as input, it did some sign extension wrongly when you give it something like this, and so it produces a netlist that does the wrong thing. And we wrote a paper about that as well. But just to break the monotonicity of this talk, I want to take a slightly different angle for reliability regarding logic synthesis tools. So I've talked already about that we don't want your logic synthesis or high-level synthesis tools to crash. You don't want them to generate the wrong result. But there's something else that engineers often want from their tools, which is stability. And what I mean by that is, if you write some, say, RTL, and then you synthesize it, you get some circuit out, okay? And then you make a tiny, tiny, tiny change to that RTL, and then you resynthesize it. Sometimes what happens is that suddenly, poof, your circuit has exploded. Suddenly the area has tripled and the performance has gone down the toilet. This is very annoying. And this is a case of what we've called instability in the synthesis tool. And we thought, oh, maybe we can do some adapt our testing techniques to try and find instabilities in these synthesis tools and maybe do something to improve those. And I just want to show you one example of a bug, a stability bug that we found, because I find this is rather fun. So it goes like this. So imagine this is a snippet of some Verilog design. We've got, these are the line numbers of your Verilog RTL, and you've declared a wire called foo. You've got some other stuff going on here, and then later on you've declared another wire called baz. Yeah, that's all we got. And then you make a tiny change, really, really tiny change, which is you remove the line break after other. That's all you do. Okay. So all I've done is I've got other and stuff are now on the same line, and everything else has shifted up. That's the only change. And yet, the full example of this, if you give this to, I think it was Yosis, this one explodes, and this one is a nice small circuit. It's crazy. Just the line break makes that difference. And what's going on is the following. What Yosis does internally is it gives a unique name for each wire that you declare. So this wire foo will be given a unique name that will be something like W95 because it's declared on line 95 underscore foo. And this wire, baz, will be internally represented as W100 baz because it was declared on line 100. You do the same down here, and you get this. And what happens internally is that the synthesis tool uses another engine internally to do some optimizations, and it optimizes each wire in turn. And the order in which it optimizes the wires is picked alphabetically based on their internal name. And alphabetically, W95 comes after W100. Whereas this way around, 95 is before 99. So the wires are being optimized in a different order because of the line break that was inserted or not inserted. And because they're optimized in a different order, you could probably just about imagine that that could mean that certain optimizations happen and certain ones don't. I mean, I don't have the full story for exactly what happens after that, but that's enough of an idea of why that line break could make the difference. It could be the butterfly wings that causes chaos. Okay, can we have more reliable logic synthesis tools that don't keep sort of miscompiling these funny test cases? Well, we're not building one directly, but we do have a colleague at Imperial called Andreas Löff who is building a verified Verilog compiler as we speak. So that's a shout out for his work. The final thing I want to talk about is the equivalence checker. So this is the work of my student Michalis. So the equivalence checker, we're talking about something where you have a design and another design. Perhaps maybe they're both Verilog RTL, maybe one is written in C, maybe one is written in Verilog, depends, but you've got two designs and you want to know, are they functionally equivalent? So you give them both to your equivalence checker and your equivalence checker should say yes or no. Equivalence checkers are important. Equivalence checkers are important. And you can see the stakes because if you look at the marketing material from companies like Synopsys, they'll talk about their equivalence checkers as giving 100% confidence, and they talk about the fact that this equivalence checker speeds up sign-off. The idea is that if your equivalence checker says that your RTL is equivalent to your C specification, and you have done all of your formal verification on your C specification, you know that that's correct, and you know that it's equivalent to this RTL, then it's basically saying, yeah, if Hector says it's okay, then go ahead, fabricate your chip, you'll be fine. Synopsys says the same kind of thing about its SLEC tool. It dramatically reduces or even eliminates the need to do simulation or verification on the RTL. You can trust the equivalence checker because it's equivalent to the C, and if the C is fine, then so will the RTL be. So the stakes are quite high because you don't want bugs being uncovered later on in that hardware design process. So we thought we'd better test these. So what we did is we built a tool that generates random designs. So this is an example of random design 1. This is an artificial example, by the way. This didn't really make a bug. But we say make A be 3, B is 5, and return 3 plus 5 plus 1. So this should return 9. And what we did then is, having generated a random design 1, we give it to a GCC, for instance, a standard C compiler, and ask what that should give. And GCC says that should give you 9. And so we make as design 2, return 9. Okay, so convoluted way of calculating a constant, straightforwardly produce that constant. These two should clearly be equivalent. We did this lots of times in the hope that sometimes we would get the equivalence checker to say no. But we were not entirely happy with that, even though we did find a few cases when it said no, when it shouldn't have. Because if the equivalence checker says no, that's a false negative. That's going to annoy the engineer. That's going to stop them proceeding to tape out. Which is bad, but it's not as bad as the other way around, false positive, where the equivalence checker says, yeah, you're good to go, but you're not, right? But we stared at this for a while and we thought, oh, actually, we can turn these into false positives, because when the equivalence checker says these are not equivalent, you look in the log file and it says in the log file, they're not equivalent because this design is equal, one of these designs is equal to 42. So we say, okay, what we'll do then is we'll take this, we'll make a new design 2 where we say return 42 and ask it again, is that equivalent to this? And this time, if the equivalence checker says yes, we found a false positive, and that's much more exciting. Or distressing, depending on your point of view. Sorry. Here's a real bug that we found. I think I won't go in full, but this is one of the values should be that, but the equivalence checker thought it was that. We wrote a paper about it with all the details, and you can see that, and it was presented at DVCon last year. Can we have more reliable equivalence checkers then that really do give you 100% confidence? Well, Michalis is building a tool called Vera. It's built and proven correct in this same mathematical proof assistant that I mentioned earlier. It works in a basic way, generating an SMT query and then solving it. Preliminary results suggest it gives decent performance on standard benchmarks, so it may be useful. And there's a subtlety related to undefined behavior that I'll talk about later if you catch me. And that's about it. So in short, just to repeat the thesis, all of these EDA tools, they're too buggy, but we can do better with more rigorous engineering, make them more suitable for safety and security critical settings. Thank you for your attention.
Hang on time. Thank you, John.